All right. All right. Good morning, guys. How are you? Or it's an afternoon or whatever it is on Monday. Can the comrades hear me?
Yes, we can hear you.
Yes. Thank you so much. Thank you. All right, comrades. Welcome to Digital Electronics. Right. In engineering or whatsoever, what you're going to be doing, we often have at our disposal several solution options. Hence, I told you guys last week that do not bank this lecture. This lecture is going to be something else. So one such option is the choice of domain for signals. I don't know whether you've heard about signals. We've been talking about electricity and magnetism, talking about fault lines, which people can't see and stuff like that. Now we want to consider analog, discrete, or time signals. Then we're gonna go to digital electronics, which is logic gates on your syllabus. It's called logic gates, Boolean functions, etc. Right. So in order to understand this thing, guys, like I say, we're gonna have to consider the benefits of working in the digital domain versus analog. By digital, we mean stuff like your cell phones, etc. Analog, we mean, how can I say, digital is the world of the computer, email and stuff. Analog is the way of long ago of Shaka Zulu when he was sending a messenger on foot to run and deliver a message instead of doing a phone call. They write a letter and say, Kijim, run. And then the guy runs until he dies before he reaches that place. Sort of like that. So we're gonna have to understand the binary representation and arithmetic. It's gonna get a little complicated in the next coming days. I'm sorry, but it is what it is. We're gonna have to understand the basic Boolean operations and apply to solve logic problems. We're gonna have to understand This other part is not for us. The sequential building blocks that I won't hammer you with this part. I will end there on Boolean operations, arithmetic, and stuff. That's where I'm gonna end. So you guys are gonna have to listen, listen and listen very careful, because kuzoshuka. All right, let's start. Let's look at signals. Right, there's what is called an analog signal. An analog signal is an electrical signal whose value of an amplitude varies analogously to some physical quantity. The signal varies continuously in both the amplitude and time. So what we mean here, this is what we mean. Amplitude, guys, is the size of something, physical size. See, that's amplitude, 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 the value there. That's what we say amplitude. So if we check here, we have V of t and we have t on the other side. With V of t and with t on the other side. So when we're talking about amplitude, we mean the physical size here. And then when they say the signal varies continuously in both the amplitude and time domains, they are meaning that at any second or millisecond in terms of amplitude, it's different, it varies. Look here. At 1 second or 2 seconds or 3 seconds or whatsoever second, right? There's a different value of the amplitude. It continues varying at whatever time. At any moment, it's different, the amplitude, right? So in terms of time, it varies differently. At a certain second, there's a certain amplitude. So both in terms of amplitude and time, it varies. At a different amplitude, it will be a different time, right? So it varies both in terms of amplitude and time domains, right? And then there's what we call discrete time signals, which varies continuously in amplitude but discretely in time, right? So check this one out. In terms of amplitude, it varies continuously, right? You see that at every interval, it's different. But in terms of time, it's discrete. It's just specific intervals. It's not continuous. It's discrete, right? It is on specific intervals, right? But in terms of amplitude, at any time, but that amplitude is dependent on time, which is discrete. So this one varies continuously in amplitude, but discretely over time, right? So there's someone who sent a message before we go forward. If I'm saying amplitude is a maximum disturbance from the rest position, is it still correct? 100% correct. 100% correct. So now let's look at a digital signal. A digital signal varies discretely in both amplitude and time domains. Right, look at this. In terms of time, it doesn't depend on what time it should be what. Look, it's always a certain interval. You see that interval? Always a certain interval, certain interval, certain interval, certain interval. Those intervals are discrete, right? It's a certain size, certain same size, certain same size, certain same size, certain same size. And then in terms of time, you look at the time. It's discrete. It's time intervals. So the amplitude is discrete. The time domain is also discrete, right? So hence we come to what is called a binary signal. Binary signal is a special case of digital. It can take on one of two discrete amplitudes, right? We come to a 1 and a 0. These are binary signals, right? It's either 1 or it's a 0, or in terms of electricity and measuring things, it's either it's 5 volts or 10 volts, or it's 0 volts or 0 volts, or minus 5 volts or minus 10 volts. So it's always a high and a low, right? 1 or 0, high or low, right? Where 1 corresponds to a high, 0 corresponds to a low, or in terms of voltages, where 5 volts represents a high, a 0 volt represents a low, or where 12 volt signal represents a high, and a minus 12 represents a low. So that's a binary signal language of the computers. I'm sure you've heard of it before, that computers operate in binary. You guys, you see a screen and you press buttons, enter, etc. For you, it's words and it's visual. But for the computer itself, it's binary. It's 1 or 0. It's a bunch of ones or a bunch of zeros. Right? It's all math for it that you're doing. If it's triple, triple, triple one, you are supposed to do this. What zeros? You're supposed to do this. Right? That's how computers operate in binary numbers. Right? So when someone says, what does discrete mean? Discrete means, right, if you understand continuous, something which is continuous, it doesn't stop, it doesn't end, it doesn't have an interval, right? It's simply interconnected throughout. But when we say something is discrete, we mean it is certain intervals which are equal. For example, look at the length or width of this and that and that and that and that. The length or width of that is what? What is it? It's the same, but it's not continuous throughout. It starts, stops, something starts again, stops, something starts again, stops, something starts again. You see, so it's discrete, like gaps in between, right? But something continuous will go like this, right? So discrete means it can be broken down into distinct intervals or distinct things. Unlike continuous, you can't break this thing into intervals, which is like that. It's continuous, right? Now, the world of analog and digital is disadvantages and advantages. But digital, guys, for example, now, I'll always use the example that I like. For some of us who are now ancestors, who are close to that, we're born in the world where we're watching videotapes. A video cassette on a VCR. That's what we're using. A videotape on a VCR. You guys nowadays, you don't need these. You have a flash stick, a memory stick, or a USB, right? Flash USB stick, right? Some of us, we had to find a bigger device, a VCR, to come and put this big cassette in there. When you're going around with it, it's so big in a way that it says, you guys don't go around carrying things anymore. You only carry a USB. It's so small, it's so nice. I can't compare. Look at the size. Ours, which is analog. This is analog. Yours is digital. For your world that you guys are in now, the millennials and the 20-somethings, right? Ours was big in size, yours is smaller, right? And then in terms of storage, you will find out that this video cassette was too big and it would be 1 gig. But you guys carry something like 32 gig in your pocket, 128 gigabytes, your phone, 256 gigabytes, your phone on a pocket. We couldn't put this video cassette in a pocket. You see, that's the lackiness of digital world, right? And then in terms of video quality and noise, have you seen how nice watching from a computer or flash, whatever you're playing? There's no struggling, reverse, rewind, fast forward. No, you just touch, it just jumps to that part where you want it to go, right? But now on us who are busy using videotapes now, you have to stop, clean. Sometimes you'd even rewind with your own hands when that VCR of yours, this rubber band mechanism was now a little bit dead. So you see the difference now. So analog versus digital signal. You see, this is continuous, right? As we were saying, somebody asking us what continuous means. You can't actually split it into different parts. That's the analog thing. But the digital signal now, look at it. It has gaps. It ends and starts at certain points, right? It's made up of ones and zeros, either a low or a high. It's discrete. Individual, it can be broken down into sections, intervals, as I said, right? But analog, you can't split something continuous like that. Right. So look at the disadvantage. If we introduce noise on an analog signal, now it's difficult to read. You see, now it is too much things. We don't know because it's continuous. It's difficult to understand. But something digital now, you either know it's a 1 or it's a 0. So if it's up there, simply it's a 1. If it's down there, whether it's down below, it's a 0. Clear cut. That's why the sound of a radio cassette of long ago had this sound. But a disc, you only hear click, which is too sharp in your ear if that CD has a scratch or something. Because digital is pure. Right? It's clear cut. Now, here is the complicated part about the digital world. I'm sure someone has already asked themselves, okay, if a digital is only a 1 and a 0, even if we introduce noise, it's a 1 and a 0. How low is that one supposed to be in order for us to say, this is a 1 indeed? Or how high is it supposed to be? So that's where there comes the measurement of it, right? So usually a high or 1 is represented by H, or it's called logic 1, right? We're gonna come to that. And then a 0 or low is usually called logic 0, right? So these devices that we use in our daily lives, a computer, whatsoever, that take a USB or take a whatsoever, or take a signal, that button that you press on a TV and you say switch on or off, that's a 1 or a low. You know that switch button of a remote on your TV, when you press, that's a high or a low. You see these gates of yours that you press and the gate opens, that's a 1 and a 0. 1 is for opening, 0 is for closing. So it's programmed in such a way that when you first press, it opens. The second press, it closes. The third press, it opens. The fourth press, it closes. It alternates. That's a simple 0 and a 1. So how high or how low is supposed to be 0? So this is how it's defined. Some devices, let's say you have a voltage of up to 10. You're from 0 volts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Some people will say from 0 to 1 to 2, right? That's considered as logic 0. It's a low, right? And then they will consider from 7 to 8 to 9, 10. If the voltage or signal is around there, they will consider that as logic 1 or high. So that means in between here where there is 3, 4, 5, 6, those are undefined. It's an undefined region. Your device gets something like a 3 or a 4, it doesn't recognize it. You won't be able to classify it as a high or as a low. So hence, that's why you see some remotes, they are different from each other. When you try to open the gate next door, it won't open with your remote. Or when you try your car keys on another car, it simply refuses. It's either there's a difference in frequency or there's a difference in the logic of the keys. Which ones are operating at what logic, which ones are operating at what sequence, right? So that's exactly what usually happens. So these are the stories that you'll be telling your young ones. You see, when I press a microwave, 30 seconds, it does 30 seconds, and you're using an LED screen, 7 segment, etc., all those logics. Why, when I press a remote, the gate goes that way, the gate comes back. I press a remote, the car opens, etc. Logic 1 and 0, digital world. So same as the output, you can now set your output to behave differently. If I'm gonna press a 1 or I expect a 1 from something, I'll simply come and define and say, let my 1 be 9 and 8 as output, and let my 0 be what? 0 and 1, such that 2 up to 7, if it comes out of my device, I don't recognize it. It's nothing that I know. I will only recognize 9 volts or 8 volts. That I will regard as a high, logic 1, that I must do something. And then if I get a 0 and a 1, then I will regard this as logic low, which I will call logic 0, which wants me to do the opposite of what I was doing at high. such that now my undefined output region is there. So that's how digital is controlled. Hence, you can see now that from the previous slide, if there is a certain noise there, we regard from somewhere there to somewhere there as a 1. And then from somewhere there to somewhere there as a 0. You realize that's why digital is clear. It's always clear cut, right? It recognizes a 1 and a 0 easily. But an analog signal, you can't. It's something else. You can't. You have to be really specific in what you are reading there. You can't guess, you can't compensate, but with a digital signal, you can compensate. Right? You can say between this value and that value is a 1, and then you give out a clear-cut 1 on your output. But on the analog signal, you have to be specific or guess 100%. So now, guys, you have to know the advantages of digital world and analog world. Digital is efficient in terms of size, like I was showing you about the memories that the USB, right? Like a USB, sorry, I'm going too far. Right, I think pressed itself. Like that, a USB flash, USB, you'll find out that it's 32 gig. It can fit in your pocket. Your phone, 256 gigabytes, can fit in your stuff. It's digital, only ones and zeros. Your computer, you can charge your phone there. It gives out an output of 5 volts. That 5 is logic 1, all right? But a cassette of a radio or a videotape of long ago, that's ancient analog examples, ancient stuff. Big cassette like that will be something like 1 gig. Imagine. The sound will be unclear. So you see the advantages of digital. It's efficient in terms of size. Power consumption, a USB only charges 5 volts to be read by a computer there, and then everything happens automatically. But our analog video cassettes, they have to have a motor which drives this thing. There must supposed to be a magnetic head reading that tape. Hey, a lot of things, too much power consumption here. But here only 5 volts and the little current as low as milliamps. Cost for processing, very cheap to process this side, expensive to process big things. Transmission, easy. We're living in the digital world now. We even use Bluetooth. We even use, what is it called? Mirror casting. You can cast from your tablet to your big TV, send via Bluetooth, send using shade, all those nice lacquer stuff. But yeah, wow. You have to take the entire day in order to tap from one end to the other end. Storage and of information, I've already talked about it. There's a large scale of storage here as compared to analog. Easier. And then in terms of integrating, look at how easy your phone integrates in this world. It integrates with your TV, with your laptop, with your car. There are cars which actually even respond to a phone nowadays. You see, but in the analog world, it doesn't integrate. You have to find a specific socket for that specific thing. Otherwise, if you don't have it, it's game over. Now, so hence, guys, we're gonna learn logic gates. That is called the binary system. That's 1 or 0, right? So you remember we talked about BJTs. We learned what BJTs are. We learned what diodes are. You understand? So digital signals can be binary, ternary, quaternary, but we are only going to concentrate on binary. That's base 2, which is 1 or 0, right? This ternary, quaternary and stuff, no, just know that it exists in the world. It's not part of it, right? So binary has become the standard method due to efficiency of implementation of two. Okay, manje sesiyaxabana manje. So you see now why I hate people who do this. I've forgotten what I was saying. I now have to start from scratch. Yes. So I was saying that we are going to concentrate on the binary system only, right? The quaternary and stuff, forget about those, right? So we're going to concentrate the standard method due to efficiency of implementation of 2 states. We're going to concentrate on this one, the binary. Like, so we can represent any number of states using the binary, base 2 or radix 2. That's what it's called, binary or base 2 or radix 2 number system, right? This is actually saying there are two states which require a binary. It's one digit, 1 or 0, right? So for instance, we usually know the base 10 number system. The number system that we know, that is 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, up to, I don't know, millions, right? We continue. That's called the base 10. But base 2 now is representing a number that we normally know into a number in the base 2 state. We usually know the base 10. So for example, right, let's take 2, for example, right? Or let's take 10. 10 is the number that we know usually. But in terms of base 2, what is it? In order to make it in terms of zeros and ones, you have to divide that number by 2. You keep the remainder. So this is what happens when I have 10 here. 10 divided by 2, right? What is that? It's 5, remainder 0, right? Then you come here and say 2 into 5. That will be what? 2, remainder 1. Then you come here and say 2 into 2. That will be 1, remainder 0. Then you come into 2, 2 into 1, that will be 0, remainder 1. Right. So this number here that you see on the right hand side, you read it going upwards. So that number is going to be 1, 0, right? 1, 0. So 10 in base 2 is 1, 0, 1, 0, base 2. See, this is the binary representation, either 1 or 0. This is 10 in the normal way that we know. So 10 represented in terms of base 2, it becomes 1, 0, 1, 0. Right. Let's find another number. For example, let's take 15. Let's take 15. What is 15 in base 2? Right. So 15 in base 2, you're going to come here and say 15 divided by 2. What's going to be that? That would be 7, remainder 1. Then you come here and say 2 into 7. What is it? It's going to be 3, remainder 1. Then you come there, 2 into 3, it's going to be 1, remainder 1. You come there and say 2 into 1 is 0, remainder 1. Then you read this number here, which is of remainders, from down there going up. That means that will be 1, 1, 1, 1, base 2. 15, the number we know in terms of binary, it's 4 ones. Right? And then we're going to go on again. Take another number again. Let's say 6. A simple number, 6. Let's use 6, a simple number. Right. We're going to say now that 6 divided by 2 into 6, 3, remainder 0. Then 2 into 3, 1, remainder 1. Then 2 into 1, 0, remainder 1. Right. Then see, we read that number like that. That's going to be 6. The number we know is going to be 1, 1, 0, base 2. All right. Do a fourth number again for the comrades to understand. What number should we do now? From you, comrades. You tell me.
25.
25. Okay. Now, there we go. Let's take 25. The comrades wants us to say 25 in terms of base 2. What is it? We're going to have 25, say, sorry. We're going to have 25, and then let's divide it by 2. 2 into 25, that's going to be 12, remainder 1. And then 2 into 12, that's going to be 6, remainder 0. 2 into 6, that's going to be 3, remainder 0. 2 into 3, that's going to be 1, remainder 1. And then 2 into 1, that's going to be 0, remainder 1. When we look at the number on the right hand side, we read it going up. That number is what? 1, 1, 0, 0, 1, base 2. So 25 is equal to 1, 1, 0, 0, 1 in terms of base 2. Right? See, guys, that's clear. So now I hope the comrades are clear now. Are the comrades stuck somewhere? Before I move on to the next thing, are the comrades stuck somewhere? Right. Since the comrades are okay, I will come here now and show you another system, what we do. For example now, guys, when we represent numbers in 2 bits, right, or binary number systems in terms of 1, that's called the binary or base 2 system, right? Every number can be represented in that system, in that term or in that system way, right? For example, the easiest is this. If you just claim, you just say, trying to annotate here. Just have to come up and say 1, 2, 3, 4, 5, 6, 7. Write down your numbers going down that way. All right. This is the number that we know, the usual form. Then in terms of 4 digits, right, you're gonna have 0, 1, 0, 1, 0, 1, 0, 1. Right. Let me make it clear. Let me clear all of this first. Let me put it this way, put it that way, and then say ta, 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 ta. Did that, ta, in ta. Change color. Okay, before change color, come we can see da 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 da. Yes, da 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 da. Right. Yeah, yeah. Right. This change color. We have 0, 1, 2, 3, 4, 5, 6, 7 natural numbers that we know. But now, in terms of binary representation, using 4 significant figures, right? Gonna have 0, 1, 0, 1, 1, 0, 1. Then you have 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. Right. Then we're gonna have 0, 0, 0, 0, 0, 2, 4, 2, 4, 6, 0, 8. Right. So just look at this now. 0 in binary numbers is these 4 zeros, right? 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is this. 6 is that. 7 is that. Did you see how I did it? Easy. I just started with the least significant figure and said 0, 1, 0, 1, 0, 1, 0, 1. And then landed had it double 0, double 1, double 0, double 1. And then I followed as a 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones. Then I followed 1, 2, 3, 4, 5, 6, 7, 8 zeros. Then continuing 1, 2, 3, 4, 5, 6, 7, 8 ones. Next one, 16 zeros, 16 ones. Next one, 32 zeros, 32 ones. But simple and straightforward. If you want to double check, right, you can check, for example, 3 in binary. We say if we want to make 3 in terms of binary, we're going to have to divide by 2. 2 into 3, we say 1, remainder 1, right? Then 2 into 1, that will be 1, that will be 0, remainder 1. So 3 in terms of binary is 1, 1. Base 2. 3 is equal to 1, 1. Look at 3. Here is 3. It's 1, 1. See, the first 2 don't matter because they are zeros. It's 1, 1, base 2, 1, 1, base 2. Right. Simple and straightforward.
Sorry, sir.
Yes.
Can you please do 15 in terms of binary, please? My phone just went off.
What should I do?
The last moment. Redo 15, please.
15.
Number 15 in terms of binary. Yes.
Okay. So here is 15. right? Just say 2 into 15, that will give you 7, remainder 1, right? 2 into 7, that will give you 3, remainder 1, right? 2 into 3, that will give you 1, remainder 1, right? 2 into 1, that will give you 0, remainder 1. Then look at this number represented by the remainder, reading it going that way. So that will be 1, 1, 1, 1. See, base 2, that's equal to 15. Clear?
Yes, clear, sir. Thank you so much.
All right, wonderful. Now, clear that. Again, let's try to go back there. Where are we? Here. Right, let's try to go back to our lecture. So, where were we? Introduction to digital electronics. Yes, we went that, we went that, we went through that, 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 went through that. This is what we're talking about. 4 states require 2 bits, 2 to the power n possibilities. This doesn't matter, but for those who love to know what they are talking about here, they are saying that, yeah, this people will get confused. Don't worry about this. Too much math. All right, these are the conversions that we're talking about that people were telling them. Right, conversions from base 10 to base 2. Remember, our natural number system that we know is base 10, but base 2 is what we're learning today. Right, so to convert a decimal number, the one that we know, into a binary, we divide repeatedly by 2 until the quotient equals 0 and not the remainders. Right, the binary value is the remainder entries taken in reverse order. That means taken in this order going up. Right, for example, they gave us an example of 108 in terms of base 2, that number 108. See what we're doing? We just say 108 divided by 2, 54, remainder 0. And then you come 54 divided by 2, 27, remainder 0. Then 27 divided by 2, 13, remainder 1. 13 divided by 2, 6, remainder 1. 6 divided by 2, 3, remainder 0. Right, 3 divided by 2, 1, remainder 1. Then 1 divided by 2, 0, remainder 1. And you read it going that way. That should be 1, 1, 0, 1, 1, 0, 0, base 2, which will be 180, base 10 that we know. So we've already done such examples, many of them. They were giving us an example like 108. Right? Clear, comrades? Eh?
Yes, sir. Clear.
All right. Now, here is a bit more complicated thing. Now we're converting fractions that are in base 10 into base 2. Right? How do we convert fractions now? For example, now we have 0.875 in base 10, the number system that we know. What is it in base 2? This time, instead of dividing, you're multiplying by 2. Right? Instead of dividing, what are you doing? You're multiplying by 2 when it's fractions or decimal. So, excuse me, you have 0.875. What is it in base 2? You're going to say 0.875 by 2, you get 0.75. Right? Look at this, 0.875 times 2. What is it? 2 times 5, 10, 0 carry 1. 2 times 7, 15 plus 1, 14 plus 1, 15, 5 carry 1. 2 times 8, 16 plus 1, 17. Right. So comma is in 3 digits, 1, 2, 3. So the answer is 1.750. Right. But now when you're doing this one after which comes after the comma is called a carry. Right. That's the one that comes there. And then you keep 0.75. There it is. Multiply it by 2 also. 0.75 by 2. What is it? 2 by 5, 10, carry 1.
1.5.
Yes, 1.5. Thank you. So this one here is called the carry. We take it and put there. Keep the 0.5. Then we have the 0.5 there, you see. And 0.5 by 2, that would be equal to 1.0, right? This one here is the one that we take, we put it there, keep the 0. That's there, we're done. So now 0.875. Instead of reading going up, we read going down now this time. That would be 111, 0.11 base 2. See, there it is. 0.875 base 10 is 0.11 in base 2. Clear, comrades? No, we should do it again.
Yes, please do it again, sir.
Here comes the trouble. All right, let's leave that side. Let's bring on the whiteboard. Right. Now, let's say you are given 0.175. Okay, first, before I do that, guys, understand one thing. If a number is represented in binary, there is no other digit except 0 or 1. If you realize that even the number 2 itself doesn't exist. 10 in base 2 is something else. 5 is something. 2 itself is something else in its base. There is no other number except 0 or 1. Those are the only digits that are there. All right. Now, let's go back to our thing. We said, let's try 0.175. Ne? Right. Take this one, for example. You come here, right? This time, what do? You multiply by 2. Right. So let's create another space where we do our rubbish writing. Say 0.175 by 2. Right. What will that be? You guys have a calculator. Tell me quickly. Comrades.
0.35.
0.35.
Yes.
Right. So this multiplied by 2, there is no carry, right? The carry is a 0 there. Carry is a 0. So we go on, keep our 0.375. 35, right? Multiply by 2. This one, what is it?
0.7.
0.7. Still, the carry is a 0. We now take our 0.7. Multiplied by 2.
0.4. Then carry is 1.
1.4, right? So we carry the 1 now. So our carry now becomes a 1. And then we keep the 0.4. Multiply by 2.
0.8.
0.8. The carry is a 0, right? And then our 0.8 multiplied by 2.
1.6.
1.6. Right. We carry the 0.6, carry the 1. Right. So you can keep going on and on and on, but depending on the number of significant figures, decimal places we want. This one is 3 after the comma, right? So our answer, we want how many? 3. So you read now, this one, instead of going down like this, we read this way, right? So our 0.175 base 10 is equal to 0.001 base 2. The other digits as well because 3 significant figures only, right? See that? Let's do another example. Choose any number. Comrades, choose any other number.
0.434.
0.434 in base 10. So you want this number to be in base 2, right? Same story, guys. Right. So this is what is gonna happen. Let's have where we do our Makakala, and then let's have our space. 0.434 by 2. What is it?
868.
0.868.
0.868.
Right. So our carry is a 0. Then 0.868 by 2. What is it?
1.736.
736. Right. So we take the 1. Our carry becomes a 1. Keep the 0.36. 0.736 by 2. What's the answer? When you multiply that by 2,
1.472.
2, like that. Our carry is a 1. We have a 1. Keep the 0.472. Right. Next, when you multiply that by 2,
0.944.
44. Our carry is a 0. Now we have 0.944. Our digit is what? Is 3 decimal places. We want 3. because now we're reading going that way. We need 1, 2, 3. So 0.434 base 10 is equal to 0.01 base 2. Clear?
Yes, sir, clear.
Clear now, comrades?
Yes, sir.
Wonderful. Now let's move on to something else. Now let's go back to our notes. Intro to digital electronics. Where are they? Can't find. There we go. Right. So, comrades, we have covered that. We have covered this. We have covered that. Now, for instance, they can give you a number like this one, 28.375, base 10. You can find 28 on its own in terms of base 2, find 0.375 on its own in terms of base 2, then add it together. They will give you a number in binary. And then vice versa, we can give you a number in binary and say convert it to decimal, right? So for example, let's say you are given 100 base 2. How do you find it in the real number system that we know? How do you work in reverse? Right. The formula for working in reverse. Right. It's easy. Right. So you multiply this by 2. So you take each digit there, that will be 0 by 2 to the power 0. Then the next one, that will be 0 by 2 to the power 1. Then the next one is that's one, the one, that will be 1 by 2 to the power 2. Right. And then add together, that 0, that is still 0. Then this 2 to the power 2 is 4, right? 4 times 1 is 4, 4, right? Then 4 plus 0 plus 0 is 4. So that will be 4. You want to double check, check. 2 divided by 4 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. There was a 0 there. That's 1, 0. See? 100 in base 2 is 4. Right. For example, let's say you are given another number. Let's say you're given, let's take this one, 1, 2, 3 in base 2. What is it in terms of base 10? Take it like this. This first one, that will be 1 times 2 to the power 0 for this one. Take this one again, that will be a 1 by 2 to the power 1 on this one. And on this one, that will be a 1 by 2 to the power 2. 2 to the power 0 is 1. 1 by 1 is equal to 1. Then 2 times 1 is 2. Then 2 to the power 2 is 4. 4 times 1 is 4. Then you add them. 4 plus 2, 6. 6 plus 1, 7. Right. So that should be 7. Want to double check? Double check. Put 7 there. 7 divided by 2 is what? 3, remainder 1. 3 divided by 2 is 1, remainder 1. Then 1 divided by 2 is 0, remainder 1. See? 1, 2, 3, base 2 is equal to 7. Done. So here is the formula. This formula will convert a number in base 2 into base 10. But I just showed you how the easier way of converting a number from the normal, from binary 2 to base 10. We have done converting from base 10 to binary 2. All right. Any questions? Clear? Clear, comrades?
On my side, I'm clear.
Where is it unclear?
Yes, sir, it is clear.
Sorry?
Yeah. It's clear, sir.
Okay, wonderful, wonderful. All right. Now, simplifying binary representation. As the magnitude of numbers increase, binary representation becomes cumbersome. Right, as you know, guys, right? As the numbers increase, like we go to 100, 1,000, 2,000, representing that number in terms of ones and zeros also becomes cumbersome. It becomes too much, right? base 2 is a natural system for binary machines, but it's tedious for us as human beings. Hence, human beings use tens, 2, normal numbers, but a computer likes those things. A computer uses binary, right? I want to annotate. It uses binary, it uses base 8, and uses base 16. That's what the computer does. It uses base 2, base 8, and base 16, right? Base 16 is the hexadecimal system. I'm sure you've heard of it. Just for knowledge purposes, you must know there's base 8, which is the octal number system, base 16, which is the hexadecimal binary. I'm sure in maths they've taught you this. If they haven't taught you this, I don't know when they are going to teach you this stuff. I was just teaching you to help understand where we are going as a basic background, instead of me just hammering you with the stuff upfront without laying the foundation. A lot of you are going to say, I'm an error, we don't know where this came from. What is it for? Applications in the outside industry. Right. So next. Right. This we know. I introduced you to how you see the hexadecimal system representing in terms of 4 significant figures. That's 1, 2, 3, 4. Right. See that octal represented in 3 digits. Binary is usually 2 digits, right? But because we go on and go on, we like using 4 so that we cover all numbers. So you see hexadecimal system, 0 is 0, 0, 1 is like that, 2, 3 as we saw, 4, 5 as we saw, 6, 7, 8, 9. But the funny thing is when we get to 10, 10 is like that in binary. This is binary, but in hexadecimal, that's A. See that? In binary, it's 1, 0, 1, 0. That's the number 10 in binary. But in hexadecimal, it's A. And then 11 is B in hexadecimal, but in binary, is this. Right? And so on. 15, as we saw, in binary, is 4 ones. Right? Remember, we did 15. It's 4 ones. But in hexadecimal, it's F. See that? And then now, there's called the binary arithmetic addition of binary numbers. Right. I hope you guys will get to understand this one. Right, here are the rules. So you are used to adding 5 plus 5 equals 10, simple. 2 plus 7 equals 9, simple, straightforward like that. But there's binary now. How do you add ones and zeros? Like the computer does, or subtract them? How do you add that? There are simple rules, right? For binary, a 0 and a 0 will give you a 0 without any carry. The carry will be 0. Remember that carry. 9 plus 2 is 11. 1 carry 1. Yeah, it's the same thing here. 0 plus 0 is a 0 carry 0. 0 plus 1 in binary is a 1 carry 0. But here comes the problem. We said in binary, you'll never find the number 2. You only find the ones and zeros, isn't it? So 1 plus 1, it can't. We're back to that primary stuff. 1 plus 1, it can't. What is it? It's sort of like a 10, but we call it, this side is in binary, we call it 2. 1 plus 1 is 2. We can't represent 2 there. So we have to put a 0, carry a 1. Right? And then when we have 3 ones, man, right? It's like a 1 plus 1, which is a 0, carry a 1, plus a 1, which is going to be a 1, carry a 1. Right. So if you master these rules, that when it's 0 and 0, you get that. When it's 0 and 1, you get that. When it's 1 and 1, you get that. When it's triple 1, you get that. Then you're easy to go. Right. For example, now, let's try numbers. Let's try some additions. Right. Here is a number here. They gave us 1. They gave us 1. Sorry, they gave us 1. Why is my pen refusing to write? Right. They gave us 1, 0, 0, 0.111 plus 1, 1, 0, 0.011. They said we must add the 2. Right. Now here comes our rules. We said when we add the 1 and the 1, what do the rules say? We put a 0, carry a 1. Right? And then when it's 1, 1, 1, 3 ones, what did they say? We put a 1, carry a 1. Then when it's 1 plus another 1, 2 ones, You put a 0, carry a 1. Then 0, 0, 0 plus 1, 1. 0, 0, 0. 0 and 1, 1. Then 1 and 1, it is 0, carry a 1. Or comma comes there. Clear? Any problems there?
Please start fresh, sir.
Yeah?
You are too fast.
Okay, okay, okay. I thought the comrades are now following. All right, let's go to the white space. All right, let's leave that one. Let's practice. Right. All right. Let's say we are given let's say you're given 1, 2, 3, 4 plus 1, 0, 0, 0. Add these two together. Right. Remember the rules. They say 0 plus 0 will give you a 0. Sum carry carry a 0. And then they say the 0 and the 1 will give you a 1, but the carry is 0, right? Then the 1 and the 1 will give you a 0, carry 1. Then 1, 2, 3, 1 plus 1 plus 1 will give you a 1 and they carry a 1. Right? Remember, those were the rules. So now let's add these two. 1 and the 0, what does it give you? It gives you a 1, carry 0. So we get a 1, we carry nothing. 1 plus 0, same rules here. It gives you a 1, carry nothing. Right? 1 plus 0, same rules here. It's a 1, carry nothing. But a 1 plus 1 now, it's a what? It gives you a sum of 0, but carry 1. So we put a 0, carry a 1. Then 0 and 1 would be a 1. See now, that's where this came from. Right, let's try another example. Let me find the eraser now. Erase. Now we're going to try another example. This is an example that we're going to try. Let's add 1, 0, 1, 0 with 1, 1, 1, 1. Yeah. It's 8 first. Right. 0 plus 1, according to the rules, gives you a 1. Right? Put a 1. 1 plus 1, what does it give you? 0, carry 1. Put a 0, carry a 1. Right? 0 plus 1, it's 1. Then 1 plus 1 from the rules, 1 plus 1 gives you a 0, carry a 1. But now when it's 3 ones, 1, 2, 3 ones, it gives you a 1 and carry a 1. So we have a 1, carry a 1. Then now there's nothing plus a 1, you get a 1. See that? Our answer will be 1, 1, 0, 0, 1. Clear, comrades?
Yes,
These are
sir.
the rules. These are the rules that you. Once you master those rules, you are simple. Right? Clear, comrades? Somebody wants us to try any
Yes.
other from their mind. Yeah? Anybody wants us to try something?
Yeah, we can try. You can try.
Benoit, what do you want us to try?
1, 0, 0, 1 plus 1, 1, 1, 1.
1. Say it what?
1, 0, 1, 0, 1, double 0, 1
Yes.
plus 1, 1, 1, 1.
Like that.
Yes, sir.
All right. Remember the rules. 0 plus 0 gives a sum of 0, carry a 0. 0 plus 1 gives a sum of 1, carry a 0. 1 plus 1 gives a sum of 0, but carry a 1. 1 plus 1 plus 1 gives a sum of 1, carry a 1. Rules. Right. Now our sum. 1 plus 1, what did it give us, guys? Let's talk.
0,
0,
0, 1.
Now 0 plus 1 plus 1.
1 carry 0.
0, carry 1.
0 carry 1. 0 plus 1 plus 1.
0 carry 1.
Wonderful. Triple ones, 1, 2, 3. What do they give us?
1.
1 carry 1, right? Which is that. Perfect, isn't it? Now the comrades have adjusted now. They now are going with me on the floor. Right. Let's clear that, comrades. Let's go back to our main focus. The main struggles. Before we go, someone did put a chart here. What if it's 4 ones? We just did 4 ones. Oh, you mean what if it's 4 ones? What are you trying to say? You're trying to say like this, like this, like this, like this. Or saying 8, this is 4 ones. You follow the rules. It's simple. You follow the rules. Let's do it. 1 plus 1 plus 1 plus 1. Let's follow the rules. 1 plus 1, what is it? Go step by step. 1 plus 1, it's 0, carry a 1.
0 carry 1.
1 plus another 1, right? It's going to give you what? A 0 again, carry a 1, right? And then that 1 plus the other 1. Follow the rules. As simple as that. You keep following the rules. Because now these things will be in line like this, isn't it? So what you do, you add these first 2 together, right? Then add these other 2 together. Take the answer from there, add it to the answer from there. Simple. But if you're going to try to do it this way, say 1 plus 1 plus 1 plus 1, for you, you will get confused. So add these 2 together, add these 2 together. Then finally add the answer from there to the answer from there. That way you are safe. You keep following those 4 rules I gave you. But if you want to add it like me, who's used to it, you say 1 plus 1 plus 1 plus 1 plus 1, all in that way. Right. Any other questions, comrades? Or I should go back to the lecture notes. Let's go back to the lecture notes. So, guys, these things are not hard. They only want you to sit down on your own, practice this thing. You will be over. No stress there. You will be fine. There's another message or someone is laughing. All right. Now, guys, I want us to go to the other part now. We've covered this. We've covered that, the carries. This one is too big, is for me, not you. I will not hammer you with that. This I can give you, right? You can try it on your own. Yeah. 6 signed magnitude representation. No, that's the mathematics department job to teach you. I'm not going to teach you that. I'm going to come to logical functions. Let's deal with logical functions, the other major part of today's story that you need to understand. That is what you see happening in real life and you've heard about, right? So, ladies and gentlemen, here, there is what is called logical functions, right? You've seen these things. In addition to the arithmetic operations that we're doing, right? A number of logical operations called Boolean functions are useful in manipulating binary numbers, right? The simplest is inversion. Have you ever heard of something called a buffer or an inverter? There's a buffer and then there's an inverter, right? An inverter is something when you give it a 0, it will give you a 1 as the output. When you give it a 1, it will give you a 0, right? These are the things that are inside your phones, inside your TVs. When you press intending for something, it gives you the reverse of something, right? Or when you want to adjust something, it gives you something. You see all these iPhones and Samsung phones that you're so excited about. They work on the grayscale and color function. They work using MATLAB, right? There's what is called image processing. It's a bunch of zeros and ones, right? You adjust a bunch of zeros at a certain corner. It adjusts the contrast, the lightness, the color, etc., the grayscale of your picture, and then it changes. These are some of the things that the binary number is used for. Because the laptop won't understand. When you're saying to a laptop, you want this picture to look greenish, whitish, it doesn't know all of that. It only knows maths. So when you press a certain function, they're saying, I want to make it brighter. It only goes and simply adds a lot of ones and subtracts some zeros there where zeros will be representing dark shade, ones will be representing one more light. Then on another function, contrast is a combination now. If there's triple ones, triple zeros, it should behave this way, that way. That's how it works. So there's what is called functions, right? Functions or Boolean functions, you must learn. Now, learn these things. When I say give the truth table of an inverter of a what, you should be able to give me how an inverter looks like in a second. Its truth table, this one. You should be able to give that in a test or exam, right? So a truth table is the table which shows the output of that system. If you're giving it a 0, for example, an inverter, you give it a 0, it will give you 1. You give it a 1, it gives you a 0, right? So it's represented like this. It's an inverter in a circuit. That's the representation in a circuit. But in real life, it's an IC, an integrated circuit, which has legs like this. You know those ICs that you see in radios. It's an IC which is like this, right? But in a circuit, when you're drawing, we can't be drawing things like that. We can represent it with just a simple line. You give it an A, it complements, gives you the opposite of A as the output. Hence, it's truth table. You give it a 0, it gives you a 1. You give it a 1, it gives you a 0. So in real life situations, this means like this. Where you have a 0, it will give you 5 volts. Where you have 5 volts input, it will give you 0 volts. That's real life situations. You realize, real life situations, right? This is something that you can use in place of an LTR or in place of what? If you want simple logic, instead of depending on the resistances of a resistor becoming high during the day and light switches off or what, use an inverter. When it's 0, 5 volts, lights are on. When it's 1, that means it's during the day. 0 volts, lights are off. So there's what is called an inverter, which gives you the opposite of what you give it, right? And then there also comes what is called an OR function, right? OR function. It depends on 2 inputs or more. It can be 3 inputs, right? For example, let's look at the 2 inputs. When it has 2 inputs, A and B, right? Then we have an output C. In a circuit, we represent it like this. This is the sign representing an OR gate. It's called an OR gate or an OR function, right? Where you have 2 inputs, A and B, and an output C, right? So if A is 0 and B is 0, it will give you 0. It's an OR function. If it's A is 0, B is 1, it will give you 1, right? If A is 1 and B is 0, it will give you a 1. If both of them are 1, it will give you a 1. It's called an OR. If one of them is on logic high, it will give you high. But if both of them are on 0, it will give you 0. See that? That's an OR gate. You can have it having 3 inputs, like having A, B, C, and an output D, such that it will now be like that. Now, here comes the Boolean algebra that we're learning. So that will be 0, 1, 0, 1. That will be 0, 0, 1, 1, 1, 2, 3, 4, something like that. So if it A0, B0, C0, it gives out a 0. If either of the 3 is 1, for example, C is 1, it will give an output of 1. If either of them is 1, it's B, it will give you 1. If either of them is 1, for example, here B and C are 1, is 1. If all of them are 1, 1s like that, it will give you a 1 output. That's an OR gate. It only gives out a 0 if all of them are zeros, but on any other situation, it will give you a high, right? That's an OR gate. This is a circuit which is used in certain situations. Like, for example, let me think. Which situation can you say? Oh, if OK or enter is pressed, that means the script must be sent on a see your WhatsApp. Sometimes they ask you on your WhatsApp, what do you want the enter bracket to represent, the enter pattern. If you press enter, do you want it to skip a line or do you want it to send the message? Right. So if you want to use enter and OK or that tick which says send on WhatsApp together, those will be your 2 functions, your enter button and that tick of sending a message. A or B. If A or B is the same as given output of 1, there is your truth table. Both of them, you didn't press them, enter or the send, it won't send. But if you press enter, it will send. If you press the tick button saying send, it will send. If you press both of them, it will send. See, that's an example of combining two buttons to do the same type of work, or combining two things out there in real life to make them work. This is how they are combined with an OR gate, right? And then there comes again something else. These are the OR function rules. These ones are simple. It's A or 0, A or 1, blah, blah, useless. What I was talking to you about is the most important stuff. Now comes the most important one in life, the AND gate, right? This is exactly what is used on an example that we talked about previously before. Right. Look at this one. This is represented like this in a second. Now, let's go back to something. See, the OR gate is a plus inside it. The OR gate, it's like A or B. So it's like A plus B plus C. But look at the AND gate now. It's multiplication. It's A by B or whatever inputs, they are multiplying each other. So what it means is that if, let's start by the representation, the name that we've been talking about, that useless. Now let's talk about the important stuff. If A or B are 0, it gives a 0. If A is 0 or B is 1, 0. If A is 1 and B is 0, 0. If only both of them are 1, then it works. Now look at the boom gate of what is it called? A mall or whatsoever, especially a mall, pavilion, gateway, etc. Overpool, right? This is how it works. Before we describe the mall, let's say there is 3 inputs. 3 inputs look this. Be now and B. Ways out A, B, C, D, L, I, like that, C 1, 1, 0, 1, 0. With 1, redo this, just destroy my. Let me do there. Change color 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1. Right. So whenever this is an in function, that means it will only give a 1 when all of them are 1. So when they are all 3 are 0, that is 0. When one of them is a 1, 0. When one of them is a 1, 0 output. 0 output. Here. 2 of them are 1, but the other one is a 0, so 0. The other one is a 0. Other 2 are on, the other one's off 0. 2 are on, are 0. All of them are on, are high. That's when you get the high. That's an AND gate, an AND function. Example now how it's used. Check the mode, as I was saying. The boom gate will do this. Is the ticket paid for? Yes, that's the 1. Does the number plate of the car is the same as the number plate on the ticket? Yes, gate open. If ticket is paid, yes, number plate is different. Someone trying to steal your ticket and get out of their car, no, don't open. Right? Number plate is the same, but ticket not paid. No, the gate will not open. But ticket paid, number plate the same, boom, gate opens. See, that's how they combine two functions to put them into use in real life. See how these functions work. But this would be the use of a camera and a computer now. The camera reads the number plate and then compares with the one on its database. The computer checks whether indeed the money entered, this guy paid. Voila. The gate opens, you're allowed to proceed and go on. If either of the two is not on, you will stay there until you rectify your situation. Unless if you're a thief now, you're breaking down the boom gate and running away. Right. Clear, ladies and gentlemen. Hey, comrade.
Yes.
Yes, sir, it's clear.
Yes, sir.
Comrade seem to be suffering a bit. I wonder what's going on. These are the end function rules we leave there. So now, in real life, there are examples now. All right, let's talk about them. NAND gate. You remember we had an AND gate, right? Before we go there, let's not confuse people. Let's go nice. Right. We said there is what is called an inverter. Right. An inverter is when you put a 1, you get a 0. You put a 0, you get a 1. That's the first one we did. Right. And then we did an OR gate, we did an AND gate. Now, when you do an AND gate and finish it, and then let's say here's your AND gate. And then now on an AND gate, you put your inverter. You have A, B, C, now D. Right. So you have an AND gate, right? And after the AND gate, you put an inverter. So which means whatever the AND gate does, you invert it, you give the opposite out of it. That's called the NAND gate. Remember now, the NAND gate only gave a 1 when all three of them were 1. It gave us an output of 1. But now if you put an inverter, that would be 0. So when all of them were not on, it gave us a 0. Now it's giving a 1. That's a NAND gate. Opposite of an AND gate. Opposite of AND. So whenever you see a small dot here, that means an inverter has been put. Right? For example, now this was an OR gate. You remember how we represented an OR gate, but now there is a dot. It's now the opposite of an OR gate. It's an NOR gate. Right? And then there comes what is called an XOR gate. This one is a bit complicated. The OR gate will only give you 1 when everything is 0, 0. The rest gives 0. A buffer. You see now, this is the most useful thing in digital electronics. You remember when I was saying sometimes it will be like this, sometimes it will be like this, but we're still able to know that this is a 1, this is a 0. Right, we use a buffer. So if we receive something like this, we put a buffer in the front, a buffer will give us a clean 1. If we give it a rippled 0, it will give us a clean 0. The buffer is something that gives you whatever you give it, but in a more clearer way. You give it 5 plus 5.06 volts, 4.98, it will give out 5 volts exactly. You give us a 0.2 or minus 1 volt, it will give a clean 0. That is what is called a buffer. It gives you whatever you give it, but pure and clear. All right. So these are called logic gates, right? Boolean functions. That's what you must know and practice. This now is Japanese for all of you. Our story has ended there. The rest is now Japanese. So ladies and gentlemen, welcome to the end of digital electronics. The rest is not use. You will die. We will leave it there. Any questions, comrades, before I discuss one last thing before I go? Any questions? Hey, comrades.
No, sir. I think you've properly marinated us today.
I think if you say so, then I'm happy. Right now, comrades, let's talk about what one of you asked me the past couple of days. They said, Minera, as I'm trying to share whiteboard, I keep making a mistake. There we go. I said, Minera, you gave us a project, but it is not clear. I posted the groups online, so everyone should be knowing their own group members by now. All right. I did put the deadline, I did put anything, but the one thing that was missing was they said, Minera, you didn't tell us or show us how we are supposed to write, how we're supposed to structure our thing. I was like, okay, fine. We'll discuss this in class to give you a clue of how you can write. Okay, let me go try and find the document where I did something similar to this. I hope I can find something that will We'll make it clear. It's all digital electronics. Electricity and magnetism, I hope tutorial. There is something similar. This was when I was still, I know ETT 1212. That's the module I was teaching first semester. Right. Let's use this. What's going on now? Gentlemen, do you still see my work? It's now black on my screen. What's going on? Okay. All right. You see this template now? Here is the template. I think it was Aisha who asked me about this. Yeah. Say the structure. You see, guys, you need to have this point one. What is the brief or aim of the project? That's one of the things that you should know. Okay, first things first. All right, let's start it this way. Point zero. On point zero, it's the group name, isn't it? Simple group name. All right. Group names, everybody there should have their name on the cover page. And then there follows the page zero, the most important one. This page is structured like this, ladies and gentlemen. It's meant to root out there are always bad apples. You know, when you have a fruit basket, you must remove the bad apple from the rest. Otherwise, it will corrupt the rest. That's what the saying says, isn't it? You got a rotten tomato, you have to take it out. It's same as us human beings. We have one of us who's bad, they are taken to jail to live like an animal because they want to be an animal, isn't it? That's how everything is done. Even as human beings were treated like that. So there are those who are called wheelbarrows in life. If you push that person and stop at the gate, they won't push or drive themselves. They wait for you to come and pick them up again and push them until you reach Edgewood campus. So if there are those people who don't work, this is the page that comes in. Right? You put your names, surnames, and student numbers, and then on the last row, the percentage contribution of each person. So if there are 7 people in the group, you all contributed equally, right? Right. 100 divided by 7, you put that number there. If there is 5 of you in a group, that means it's 100% divided by 5, which means each person contributed 20%. That's equal contribution, right? So if you get 70%, everyone gets 70%. If you get 90, everyone gets 90 because you all contributed equal. But however, there are those ones which we are trying to fix, which like not working, and then at the end of the day, they come to claim. So if you actually show them off from the very beginning, they have no excuse to say, no, you were talking behind their selves or their back or whatsoever. You put your percentage. For example, if there's 5 of you, someone decides not to come, they work maybe 10%, which means now you are left with 90%. So that 90 is divided by 4, right? By 4%, right? So which means 4 then into 9, that will be 2 remainder 1, that will be 2. So that's something like 22.5. So that means each of you contributed 22.5%. That guy only came on the first meeting and disappeared. You give him that respectful 10% of his. So if the group gets 80, that means 22.5% is equivalent to 80. But this 10%, we're going to come and say 10 over 22.5 by 80, right? So you will get something like 30 or 40 or 50%. It will be equal to his contribution, right? So that's fair. If a comrade decides not to come, that's 0, right? Which means the other 4, you have 100 divided by 4, you have 25% contribution. They get their 80s nicely. He gets a 0. That's the law. So do not forget that page, especially in a group which has problems. So if you're in a group where a person has problems, that's how you take care of them. You write that
Sorry,
page,
sir.
only one. Yes.
I'm sorry to disturb you on that one. On this project, how do we find those, or whose responsibility is it to find other group members? Like we've tried to find other people, like writing them an email according to their student numbers, like how we are mixed together there in groups on Learn 2022. We've tried to email some people, but they haven't responded. Like in my group, I think right now the people I was able to be in contact with were 3. So what about the rest of other people, like who we can't get hold of?
All right, that's where I was going. At least you're following. Thank you. So you know what you do. The same way that I deal with you is the same way that you deal with them. You know what I do. If I find out that you're not submitting or participating in class and it's bothering me, I will simply write you an email like you did. If I find that you are not responding, you know what I do. I write another email and I CC you to the TLC office, such that when you come later in future, you want to claim that I never even tried to put an effort in helping you, you'll be stabbing yourself. So you do the same thing. You have emailed them, right? They are not responding. You simply take that email, forward it to me. When you're forwarding it to me, copy them again on the email. So on the day that you were giving them a clean 0, the evidence will follow them. You understand?
Yes, sir. And another thing, sir, in this
Yes.
project, we are supposed to build something, right?
I'll get to that part. We're first trying to solve this the issue of cheating and the issue of people using other people, which is not fair.
Yes, I'm
So-
still on that one.
Yeah.
Yes,
So
we're
now-
supposed to build something like when we're supposed to build something like people, some of them, they haven't came back from home. Like, how do we work with those people who are still at home, but yet we're a group, we're supposed to meet and do this project together as a group? How do we work with people who are at home, who haven't came back?
That's where I'm going, but it seems you have overtaken my teaching of the template now. You are way far ahead of me than me. I was coming nicely to explain all of those things, but now you are way faster than me. So first of all, I say to you, page 0, we are solving those who do not attend, right? Who do not communicate with you, who do not want to do anything, right? And then on that note, we will get to the point that you are talking about, which is the point of what is called working together, what. So guys, first you have the point 0, the page 0 that I talked about. Second, now, you have to have your aim of the project, right? Or your brief of the project that is marked on its own, right? Next, you have the list of materials that you're going to use or that are needed for the prac, right? Thirdly, you're going to have to estimate how much those cost. As a facilitator, you're going to be doing your own practicals at school. The lab tech won't come to you in that high school or primary school where you'll be and say to you, no, you're supposed to use these materials and this and this. No, you are the one who plans those work, those pracs, those facilities for those kids. So you propose your own plan with this budget cost, you give it to the lab tech. The lab tech then goes out to buy or sends to management to say, no, the budget is there or what. If the budget is there, they come back to you. That's you being a facilitator. So, right, you have your page 0, you have your page 1, your aim of the project, you have the list of materials that you need, then you have the cost that you estimate. There's Google, you can go anywhere to ask, so many parts sell parts, but there's no need for you to go there. You just go to Google, you can find an estimate cost of that. And then now, here comes the question where our gentleman was asking us, which is a bit tricky, right? Because some people live in Umlas, right? And then someone else lives in Glenwood. And then someone else is in Pietermaritzburg. And then someone else is at Kwatuguza. I understand. So it's way totally impossible for you to meet and build such a thing. So what you do, that's where Aisha, I think, was also asking me, like, how are we going to write this? That comes to what is called the lesson plan. I'm sure you've already seen that, right? So hence your brief, your materials, your estimation of cost, right? So from there on your lesson plan, you write now, what is it that you want to achieve? That should have been part of your main brief, right? What is it that you want to achieve, right? And then what is it that you want the children to do, right? What is it that you expect them to learn or to uncover at the end of the day? So now here on step 4 and step 5, step 4 especially where it says photographs of our design, this step is not there for you. On that step, this is where you tell us what you expect to happen there, what you expect the children to learn. And then from there, that's where you put examples like me or like one other friend of yours was asking me, can you give us at least even some websites where we can find this or someone? That's where you give me an example of a website or web page where you found out about our project, where it's discussed, or YouTube where it's being tested, there's a link and it's working, or Daily Motion website, whatsoever, or textbook, whatever reference that is there, I can read and find it, right? And then on step 5, what criteria did that you want your children, right? Then on step 6, where it says what worked well, it's you now as a facilitator like me. You are saying if it works well, it should behave like this and like that and like that. If it works badly, it must be not totally working, blah, blah, blah. 50% mark will be somewhere around. You tell us they are your students, right? And then number 8, 7, what challenges do you expect your students to face, right? And then 8, how did we deal with those challenges? How are you going to deal with your students' challenges? For instance, I am meeting a challenge right now. The first challenge that I've met is that you guys are not staying near each other, right? How do I solve that? Simple. Zoom. You call each other on Zoom, you use emails, right? These are the official university communicating protocols. WhatsApp is not official. Email and Zoom is official. And a student is expected to check their emails at least twice a day. The day you come to campus in the morning before you sleep, because announcements come in. All right, those are the official protocols, or Microsoft Teams. And the nicest thing, you can also use Learn 2022. There's a messaging service there. You can write a message directed to your own friend. Lucky thing again, if you finish your data, but you have Global Protect, you can use Learn 2022. The email system will work when global system is on. That I've tested and proved before. I turn my Global Protect on, the email system works of school. So, challenges that you expect to meet, I have met my challenge. And I found out that you guys are far away from each other. Materials also are a problem. What did I do? Instead of making you build that project, I've converted it into a lesson plan. I'm facilitating now, thinking outside the box. You are writing a lesson plan for your own students. You are preparing a prac for your own students. That prac was supposed to be done by you, but we have problems. We've converted it into a lesson plan, which doesn't require the problems you are seeing. So what would we do differently in the future? What would you expect your students to do differently in the future? All right. How well did we work as a team? That is me now who's assessing you. You guys are going to tell me how well you thought you worked as a team. But me now, when I'm marking, I will know the different sections of writing there on that report that this was a well-coordinated group or no. Plus that mark table that you gave me, it will tell me that no, there was one person, which means the other ones are safe. This one must die because of their own problems, right? So how well did the team work? This is easy to tell. For instance, you as a facilitator out there, if you say your guys must present to you, right? You just listen to their presentation. The one who didn't study and who doesn't know the information about the presentation, you will hear them. There will be too much stammering and stuttering and nonsense. Then you identify that, no, this is the rotten apple here. Right, it's easy, that one. So to repeat again, point 1, do not forget that important page. And do not forget that if you try to contact someone, you must have evidence. That's why we do not like talking around people's backs. You email them, they don't respond. You email them, they don't respond. You copy me on the email. University police, everyone is supposed to check their emails twice a day. I will check the email, I see it. Then when the day of submission comes, you submit with you giving them 10%. They try to come out to cry or what, we'll give them a clear 10%. No stress there. Step 2, you start writing your lesson plan. What was the brief or aim of the project that you want the students to do? Tell us what materials are they going to use. Give us how much cost are you expecting to see. Tell us. Now, photographs of your design and what it's there on Google, right? What websites are there? Assisting material. What diagrams are you going to put? Example, I gave you a diagram that's expected, right? So you also draw your own diagram. I gave you a diagram of a prac. You create your own diagram of the project. It's yours. It's your research. Get the diagram ready for your kids, right? What criteria did you use in your design? What methodology are you going to use in your design? What steps do you expect them to take? You list those down. What worked well? What do you think is going to work well? What are your expectations? You are the facilitator. So if you research about it, you must know what's going to end well, what's not going to end well. What challenges did they face? Are they going to face? I've already showed you one challenge that I've met from you, how I'm handling it. All right. And then what would we do differently in the future? Find solutions to curb those challenges and problems. What do you expect to do, or how are you going to solve them in the future? How well did your teams work? Then you tell us how you find out how well your teams work. Simple and straightforward. Right. So this was what Aisha asked me about during the week, that I wanted to clarify that it's going to pose a challenge on people. And as our comrade here, the gentleman, reminded us that no, Minera, there's still another problem, the building part. No, we're going to put it as a lesson plan. It's called the lesson plan. Right. These are the kinds of questions that you meet in the practical part of the exam. When we say, all right, give us your lesson plan or your criteria for your grade 9s or 8, then you're going to have to give us a brief story of everything that this template is trying to ask you to describe. Right. Any questions, comrades?
Yes, sir.
Yes, go ahead, my guy.
So say if I'm getting you correctly, you are talking about that design project that is due on 5 November, right?
Yes.
So that right now we are not building anything, we are writing a lesson plan.
Yes.
Oh, perfect.
Any other questions, guys?
Oh, sorry, sir.
Yes, go ahead.
Can I also ask regarding this writing? So we are no longer doing the segregation whereby we're gonna be designing this thing on campus. We are no longer doing that.
You're not gonna build this thing, right? You're not gonna build this thing. You're gonna do a lesson plan. A lesson plan has to have all of the methodology of how you're going to build this. That's why it's saying there, photographs of your design, right? Which means we want your methodology, how you're going to design it, right? You can use pictures and stuff. You can learn from Google and stuff, right?
Yes,
But
sir.
in terms of building, you're not going to physically build. It's a lesson plan. You are preparing your students for a prac. But when you're preparing them, you are behind the idea of knowing what's going to happen, etc., blah, 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 right?
Yes, sir.
There's also some text here on chat. So this
Can
means,
I-
right, just to make it clear, sorry, let me read this. This is not the practical. The practical and the project are two different things. Very clear. A project is a project. So on its own, you are writing a lesson plan. A practical happens every Wednesday by groups, which you chose, right? So on this Wednesday, there will be a prac where you're gonna come. The project is posted on its own. It's its own different thing. So say, are we writing lesson plan using template questions? That was a guide for you on what the important most aspects which are needed are. So whatever is in that template should help you to write more better. Mine is just a template. You are going to write better than mine. But your basic template, your basic report must contain all of those things that are in that template. You can change the order and use your own order. You can write in a different style. But as long as those points that are in the template are there in your report, it's fine. Right, then go ahead, who was trying to speak.
Oh, it was me. I was just clarifying. I think that the person who asked you a question before you read my question in the chat, why he said, so sir, we're not coming to campus, because people were confusing this with the prac. They think that this project is the prac, and now that you're saying we're not going to build for the project, they're thinking we're not doing a practical anymore on campus, but it's two different things.
Two different things. A project and a practical is two different things. And it's written on the course outline. A project is its own mark. Practical is its own mark. It's two distinct things. Any other questions?
Sorry, sir.
Yes, Minel.
I think Sarah there is not getting it. We are not confusing a practical and a project. We know that very clearly. We know clearly what a practical is and what
Can I
a
answer?
project is.
Can I answer?
Yes, sir.
We are a family here, my guy. It's not all about trying to prove a point that someone said something, there is something said that. You see, these are the statements that are wasting our times. She made a mistake on her part. You can correct it directly by via messaging her, not on this platform. On this platform, we want educational purposes, something which will push us forward. The external arguments that you guys like to make like last week, please, can we put them aside? Direct it to whoever you are talking to, not to us. Some of us were here for pure business. You feel that someone has offended you in the way that they speak. There is direct message. Direct it there, not here. That's why on WhatsApp I closed the template, because I do not want it to be involved in unnecessary talks, which are only gonna confuse people in what the main important thing is all about. The main important thing is about differentiating that there is a project and a practical. And after that, the main point was to explain how the project is supposed to be written as a lesson plan, of which the lesson plan has been discussed, how people are supposed to write it, how they are supposed to communicate, right? And one important factor that I left out is this one. It is the responsibility of every group member that the report is submitted on time. So if there are 7 members, one of you or 2 of you or 3 of you can have load shedding, but there's no way all 7 of you stay in one place, as you said, as you pointedly made it clear to me that some are in what who's are some are where, depending on our geographical locations. So it is the entire group's responsibility that the report is what is submitted. You can choose a group leader amongst yourselves. It's your own business, not ours, on your own. But there, when you're submitting, you must check on your guy that you said who must submit for us. You must check on Len. Did you really submit 10 minutes before? If not, then one of you, it's your own responsibility to submit too. Right? So make sure that you check, because if you come next time and you're sending me an email, no, we're waiting for Amahle didn't submit because she had load shedding. That's not how ShopRite or university or anywhere works. One of them goes down, is sick or dies, the other ones take over. That's how the world works. You don't go to a bank and they tell you today because the manager is sick, you can't get your money. No ways. That's how a team works. One of you goes sick, he has a death in the family, something bad happens, the rest of you should be able to project up. You're going to meet other teachers, you're going to build other team building events and etc. in the schools out there. You're going to have to carry your friends whenever there is reason to. So be careful of such. But otherwise, gents, if there is nothing, ladies and gentlemen, which is related to what's important that you need to ask me here, we can call it a day and go. But if there is something that pertains to propelling us forward in terms of educational purposes, you can ask me the question. I'm here to help. And besides, guys, this has been what is it called? One of our last intense lectures. From now onwards, we're gonna be revising. It's easy stuff. We've covered almost everything on the syllabus. What's left is just small stuff we're gonna talk about in brief on the other coming days, but our syllabus is clear now. So it's time for people to request, Minera, can you repeat that topic? Or can you assist us somewhere there and there? Right. But otherwise, we're left with assessments, just a little revision, touch-ups here and there, and then we're done. Otherwise, we're all good, right?
Yes, sir.
All right. Thank you guys for a wonderful day. I hope you two enjoy your day. Let's call it a day and let's see ourselves tomorrow in the morning. Tomorrow in the morning, yes. And then we'll see ourselves on Wednesday in the park, where we see each other face to face at 2 o'clock. Otherwise, have a great week ahead of you. Goodbye.
Bye, bye.
Goodbye, sir. Have a great day.
Danke, danke, bye, danke.